In a simple electrolysis, we reduce our cation, we oxidize our anion at the anode and cathode, and we just see how much voltage is required to occur. Sometimes we have a more complex example. Occasionally, you'll have a mixture of different cations and anions, and we'll do an example of that in the problem. But really, the most common thing is to realize we have an aqueous solution. So we'll try to do a lab related to this, as well as doing these examples here together. But when we have an aqueous solution, we have a couple different oxidation and reduction reactions that could occur. If I had just pure water, water can also be oxidized or reduced. Right here, instead of circling my hydrogen as my middle, I have shown that right there, I have a reduction reaction that creates water, and then I have a reduction reaction that uses water. So I can reduce water, gain 2 electrons, which causes me to make hydrogen gas and produces the hydroxide ion, but that requires 0.83 volts. Taking oxygen gas and hydrogen ion and gaining 4 electrons to make water produces, 1.23 volts. Or if I was going to take this water and think about it the other direction, that water and go back the other way to oxidize the water or have it lose electrons, it could make oxygen gas and it could make hydrogen ion. Of course, that backwards process, instead of having this reduction potential, would require some energy because it'd be an oxidation. So with pure water, with no other ions there, and it doesn't really work without ions, and that's kind of beyond what we'll look at. But if I had pure water and I put voltage into it, the water could be oxidized to make oxygen gas and hydrogen ion, and the water could be reduced to make hydrogen gas, and it could make the hydroxide ion. So when we look at that, we have two possible reactions of how we can react or how we can involve water in a redox reaction. When we look at an aqueous solution, we're thinking about, well, what is the reduction or the gaining of electrons that's most likely to occur? Water can be reduced, but it requires 0.83 volts. So we want to think, is it more favorable to reduce the water or to reduce the cation that's floating around in the solution? So we compare the reduction potential of water to the reduction potential of our cation, and then we see what's more favorable. For our anion, if it's a negative anion, that would be listed over here. Maybe that's going to be oxidized, or maybe water is actually the more favorable of the oxidation. In either case, we would be comparing the reduction potential and looking at, in this case, what is more negative, because we want to be oxidizing it. Ki is a great example of this, and we'll find the different components over here. I know that it's blurry, but we're thinking about what all is in the solution. If I have Ki, which is what this is, that means in the solution I have potassium ions, water molecules, iodide ions, and water molecules. I don't have potassium solid, nor hydrogen, nor hydroxide, nor iodine solid, nor oxygen or hydrogen ions yet. I have these two and I have those two. So I am looking for the reduction. Is it easier to reduce that potassium? That's the bottom line right down there, I believe, or near the bottom. Or is it easier to reduce my water? Well, the water only requires 0.83 volts, and potassium's all the way down here near the bottom, requiring significantly more. I think I wrote the wrong number there, in fact. This should even be 0.292. Sorry. So the water has a more positive value, or even though it's unfavorable, it's more favorable than the potassium, so it requires less voltage input, and that one's likely to be reduced. And if I look at my oxidation, up here I have water. The reduction is positive 1.23, so we would be thinking the other way. But iodine's right in this middle ballpark, 0.53. Iodine is less positive in terms of reduction, which means more likely to be oxidized. So out of these, the water is easier to reduce, but the iodine is easier to oxidize. So the water is my reduction. It goes to hydrogen and hydroxide according to this reaction. My iodide is going to be oxidized and turns into iodine according to this reaction. I take my 0.83 or negative 0.83 minus the 0.53 and see that I need at least 1.36 volts of input. Up here, we would be producing hydrogen gas. Hydrogen gas. It doesn't show it, but we would be making hydroxide solution. And then here it shows iodine as a gas. Iodine is actually much more commonly a solid. So it can change states, especially if this is heating up. But the more important thing with the iodine would be a potential color change. So for all of these, some signs of reaction we're often looking at is a formation of a gas. Well, we've got bubbling, and the fact that it's bubbling at R, remember that's our reduction and our cathode, because it's happening at the cathode, we can know that the reduction is what's producing the gas. We could see maybe the hydroxide here changing the color of an indicator. We could have phenolphthalein and see that happen. And then color change, iodine and some of these other things also produce a solid. There are more complicated examples where we get into kinetics, over voltage, all of those things, but we're going to really focus on these more straightforward ones. So the key here in an aqueous solution or in a mixture is looking at what are all of the things that can be reduced, what are all of the things that can be oxidized, and which still is the most favorable of the options presented. It's going to be really important that we look at some of these examples and understand how to apply that chart and those thoughts.